All right, let's get started. So, as a reminder, we're working on task 8. And we want to find this degrees of separation between two actors. How many movies do we have to traverse to get from one actor to another? Let's talk about how to do that. Because we really didn't talk about how to do it yet. Before we get into it, any questions? Yep. Not by default, but if you email me, I can open it up. All right, so, and this is our last, that's what else I wanted to say. On Friday, the slides are a memory diagram. I probably won't do the memory diagram. I plan on doing like live coding and debugging and just anything I think will help with the homework a little bit, or just helping with more debugger practice, something like that. Since we don't have a quiz on graphs this semester, the memory diagram isn't the most useful thing. So that said, today is the last piece of learning objective content for the course. After today, you can do task 8. You'll have everything you need to do task 8. And Friday, we'll just do examples and stuff to help out. And by default, I might just do the memory diagram anyway. I don't know. It's there. So after this, all 8 tasks are on the table. Bless you. So let's do it. Hi, Tomato. Pathfinding with breadth first search. Yep.
So what are we getting up to halfway through? What's like the
It's on the schedule. It's the state pattern. So there's an AO task. There's a 9th task that's just for application objectives. And that's what we'll do the week after the break. And the next week, which is the last week of classes already, is up for votes. I got to create that Piazza post so we can vote on what to do that week. All right, pathfinding with breadth first search. Let's talk about it. So a few definitions before we get in, which those of you in 191 have these definitions, but let's get them out there for anyone not taking 191. A path, we talked about last time. A path is a sequence of nodes where each consecutive pair of nodes are connected by an edge. So this is a path in the graph. There's an edge connecting all those nodes. And let's extend this definition a little bit and say the length of a path is the number of edges in the path, which is equal to the number of nodes in the path minus 1. So this 1, 2, 3, 4, 5, 6, 6 edges in this path. That's a path of length 6. Distance between two nodes is the length of a shortest path between them. There might be multiple shortest paths, but the length of a shortest path, not necessarily the shortest path, that's going to be the distance between the nodes. So Lincoln and SRI, there is this path of length 6 connecting them, but there's also a path of length 3 right here connecting these two nodes, 1, 2, 3. So the distance between these two nodes is 3, because try as we might, we can stare at this all day, we're never going to find a path between those two nodes that's shorter than 3. So 3 is going to be their distance. And if two nodes are connected by an edge, like BBN and RAND, their distance is 1. You can get to a node between the two nodes following one edge. That's a distance of 1. And the distance between a node and itself is going to be 0. You don't have to traverse any edges to get from a node to itself. And this is what we want to find. This is what we want to find is distance. So to make sure the parallels are crystal clear, hopefully at least, for your homework, your nodes are your actors or cast members, and two cast members are connected by an edge if they starred in a movie together. So step 1 of the assignment, which I'm not going to go over too much. I'll go in a little bit of depth right now, but that's about it, of building the graph. Step 1, build a graph. So you're going through all your movies, and for each movie, all of the cast members, for each pair of cast members in that movie, you're going to add an edge on your graph connecting those two cast members. You can use the graph class that's already given to you, so it's a matter of creating a graph and then calling add edge on every pair of cast members in each movie. That's going to build your graph where cast members are connected if they're in a movie. And then the distance between two actors in that graph is their degrees of separation. It's exactly their degrees of separation. Because each edge represents a movie, and it's how many movies you have to traverse to get from one actor to the other. So our task for task A is 1, build the graph, which isn't the hardest part of the homework. There's a few little just programming challenges there, but nothing too much. You're at the end of 116. I'm confident you can all handle that one. And then the bigger challenge is figuring out that distance number. That's what we're going to spend the rest of today's lecture talking about, because that one is a lot more difficult, so I got to walk you through it a bit more. So we want to find the distance. If we find the distance, not necessarily a path between two actors, but a shortest path between two actors. So if there's a path of 4 movies connecting these two actors, but there is also a path of 3, we want to make sure we get that 3. We want to make sure we find the shortest path, the distance of a shortest path between two actors. So this is our goal. Finding the distance between two nodes in a graph is exactly what we need to figure out for task 8. So how do we do that? We're going to use breadth first search. We're only going to talk about one graph algorithm, that's breadth first search. We talk about what graphs are, and today we're going to talk all about breadth first search. So breadth first search better be the answer, because that's all we got. We don't really have anything else. I could just leave it up to your own devices and say, figure it out, but I think that's a little bit beyond 116. I'm going to walk you through the algorithm and tell you how to use this algorithm to find distance. That's what we want to do today. And we're going to go through breadth first search 3 times today. We already went through it 1 time on Monday, but I just really hand waved through and said, visit the neighbors and the neighbors of the neighbors, and then voila, it's done. That doesn't help you code that up. There's no implementation details there. There's really vague, really hard to turn that into a method. So let's go through it a few more times, and each time we're going to add another layer of complexity. It's actually the second one that's going to be the most important for you, but for what it's worth. So let's run through this again. And now I'm going to keep track of a little bit more information. Instead of just marking nodes as visited and keeping track of the connected component of a node, I'm going to visualize it like this. I'm going to start at Carnegie, because I don't feel like starting at UCLA again. I'm going to start at a different node, Carnegie. And each time I visit a node, I'm going to build a second graph that contains all the nodes that I'm visiting and all the edges that I used to visit each node. So Carnegie, and I'm going to be very careful with the way that I display this new graph. By the way, graphs don't have any concept of the head of a graph or the root of a graph like we do in linked lists and trees. These nodes can be anywhere. I can rearrange these nodes. Like, it was completely arbitrary that I decided to represent this graph exactly in this way with these nodes in these positions. So I can rearrange these. So in the new graph that I build, I'm going to put the nodes in different places visually. The root node, the first node, or the starting node for BFS, I'm going to put up at the top of this new graph that I'm building. And then each time I explore a new node, I'm going to draw them visually lower in this graph. So every time I take an edge to discover a new node, I'm going to go down visually on the slide. So case in Harvard, they're going to find Lincoln and BBN using these edges. So we have these edges going down. And then BBN and Lincoln are going to fight over MIT. This is where ties are going to be broken arbitrarily when there's multiple paths. Oh, actually, I haven't mentioned that yet, have I? But ties are going to be broken arbitrarily when 2 different nodes at the same, this is neighbors of the neighbors of the neighbors of the starting node. We're going to have a tie here. In these cases, we can break the tie arbitrarily. So we got to pick one of these 2 edges to take. I'm going to choose Lincoln to discover MIT. And then this edge will not be used in the final graph. So this edge that does exist, I'm not going to put in my final graph here because I didn't use it in the algorithm. I didn't use it to discover a new node. So I just don't put it in that graph. And when I say this tie is broken arbitrarily, it's broken arbitrarily in the slide. Like, I just have to pick one because I'm going through the algorithm manually. In your code, you don't have to have any logic in your code that says, this is how we're going to break ties. It'll just kind of happen naturally. It'll just be whichever one happens to be processed first by your code If Lincoln's processed first, it'll take this edge, and then BBN will ignore MIT because it's already been explored, or vice versa. If your algorithm finds BBN first and explores its neighbors first, then that's the edge that'll be used. Yeah. Right, it won't matter. Because we're eventually going to build up to distance. We're going to use this to find distance. And whether we find this path, 1, 2, 3, or this path, 1, 2, 3, your degrees of separation are going to be the same int. So the number is going to be the same. The distance, whenever there's ties like that, the distance will always be the same no matter how the tie is broken. And since it's distance that we're concerned with, that's going to be good for us. We don't have to care which path was actually taken. MIT finds Utah, and then Rand finds 3 other nodes. Again, always going down whenever I discover a new node. Then SRI and Stanford. SRI, there's a lot of nodes fighting over SRI. We can discover it from 3 different nodes. I chose Utah. And then UCLA is the only choice for Stanford. UCLA has to discover Stanford. So what I end up with is a second graph. It has all the nodes of my original graph, or in general, all of the nodes of the connected component of the starting node, if it's a non-connected graph. And this graph happens to be a tree. So it's not a tree in the sense where we had node objects and references to other nodes in the heap. It is still a graph, but it's a graph that is a tree in the theoretical sense because it has no cycles. If we added any of those extra edges, we would have cycles in this graph, but breadth first search ignored any edge that would have created a cycle if it were added. So we have a tree that represents our graph with only the edges that were used during the run of breadth first search, and it has levels. So the way we drew this visually, where each edge goes down, and if we use that fact and then label these as levels, where the starting node is on level 0, and every time we go down using an edge, we increase the level number, what we get is this very convenient fact that the level number is exactly equal to the distance of that node to the starting node. So these nodes at level 3, MIT and Rand, have distance 3 from Carnegie, and these edges that we traveled to get there are always going to be a shortest path between the starting node and that node. So this path here to Stanford is a shortest path from Carnegie to Stanford. Guaranteed by the algorithm. This is a nice, very nice, convenient property of breadth first search, that the edges that we travel to discover nodes will be part of the shortest path from the starting node to that node. So we can run breadth first search and get our distance information, which is what we're after. So that's really convenient. And we can stare at this forever. Carnegie, for example, Carnegie to SRI. We know the distance is 5, which seems pretty high for a graph like this. We can see the path that we took. Not like that. Oh, I chose SRI. SRI, that path of length 5. And we can stare at this all day. You're never going to find a path from Carnegie to SRI of length less than 5. Because breadth first search guarantees that it doesn't exist. If it did exist, breadth first search would have found it, and SRI would have been up a higher level. Since we're exploring the neighbors, then the neighbors of the neighbors, we're always going to find the shortest path from the starting node to a node, or a shortest path. Like, for example, for MIT is distance 3 from Carnegie. Whether we've discovered it from Lincoln or BBN, it's still going to end up on level 3 with distance 3. Okay, great. But I said one really kind of BS thing here. Whenever you discover a new node, draw it visually lower on the slide. How the hell do you do that in your code? We don't have any concept of that in our code, or at least nothing that's easy to program. We would have to get into computer vision and a whole bunch of AI and stuff to process this. It's not going to happen. We're not doing it that way. So we want to do the same idea, but in a way that we can actually code a lot easier, something that doesn't rely on visualization. This is nice for our human eyes, so we can visualize all this information. Not good for a computer. So let's take the same idea, and instead of drawing nodes visually lower on the slide, we're going to create a data structure which is going to keep track of this level information, which from now on I'm just going to call distance. It's keeping track of our distance information. So let's keep track of that information, and we're going to do that with a whole mess of data structures, which is, in my opinion, quite fun. Do we have to worry about choosing our starting node, like in the case where there's a break in the graph, essentially two split graphs? I'll say no. I'll say no. And let me explain. So what you're expected to do in general, yeah. But in task 8, what you have to do for this course, no. You're given two actors. You want to find the distance between those two actors. Either those actors are connected or they're not. So what you'll do is choose one of those two as your starting node. It doesn't matter which one. And if they're not connected, you're never going to find the other one no matter what. And there's really nothing you can do about that one. But if they are connected, it doesn't matter which one's your starting node. Choose one as your starting node and find the distance to the other one, or vice versa. Choose this one as your starting node and find the distance to this one. Either way, it's going to work out. So for the confines of this course, you don't have to worry about that. But in general, depending on your application, your specific application, that might be something you have to think about. If you have an unconnected graph, you might want to find distances in each of the connected components. It's a nice edge case that you should be thinking about that not really going to be too concerned with in 116. Either the two actors are connected or they're not. If they're not connected, you're returning -1. So you do have to detect that they're not connected, but we're not going crazy with it. Okay, and this takes a whole mess of data structures. Personally, I really like graphs as like the capstone of the data structure portion of this course, because we use a lot of data structures. To represent a graph itself, we have a hash map of values to array lists of values. We already used 2 data structures just to represent a graph, and we're going to use 3 more data structures in our run of breadth first search. So we got like 5 total data structures at a minimum that we're going to use to get the job done of task 8. It's really a good capstone of all the data structures we've seen. Not all of them. We're not going to use trees or linked lists unless you want to. But let's go over these 3 data structures. So this is how we're going to set up breadth first search in our code and use breadth first search to visit the nodes in the right order and keep track of all the distances of those nodes, the distance from the starting node to each node in the graph. So these 3 data structures. 1, a queue. Way back when we learned about queues, we finally get to use one. A queue, we're going to use this to keep track of the order in which we're going to visit the nodes. For this, you have quite a few options. You can use the queue class from the examples repo, the one that we built on a linked list. That's fine. You can use Java's built-in queue class. I'm fine if you do that. Usually some of you like to use Java's built-in stuff for other reasons, and I'm not thrilled about that. But this one, yeah, go ahead. Just use the Java queue if that's what you want to do. What I mean by that, some of you import Java's linked lists to try to get around understanding linked lists. The tests are a little more resilient to that these days, but y'all still have been trying to cheese it. But anyway, queue, I don't care about in this case. I just want to know, can you code up breadth first search? I'll explain breadth first search. Can you turn that into code? That's what I want you to do for task 8. So I don't care what queue you use. Your third option for a queue is just use like an array list or linked list or your favorite data structure and just use it as a queue. It doesn't have to necessarily be a queue, but it has to be used as a queue. You have to enqueue at one end and dequeue at the other end. If you want to use an array list for that, knock yourself out. It's not efficient, but hey, it's 116. We're going to save efficiency for CC 250. That's where you're really going to be concerned with the efficiency. So a queue, and this is going to keep track of the order in which the nodes are going to be visited. And because it's a queue, it's going to exactly do what we want for breadth first search. We're going to visit the nodes in a very particular order that's going to get us our distance numbers. And fun fact, if we swap this queue out for a stack, we're going to get depth first search instead of breadth first search. The data structure we use here to keep track of the ordering really changes the entire algorithm if we use a different data structure there. So Q is what we want. That's going to get us our distance numbers. Depth first search does not get us distance numbers, and it's just not useful in the context of task 8 or anything we're doing in 116. Which is sad. I kind of want to talk about depth first search in 116, but I don't have a fun way to put it in an assignment to have any useful information out of it. It would literally just be visiting all the nodes in a graph in some order, some kind of arbitrary order. Which, why not just use breadth first search then? And then second data structure is some data structure. I've seen lots of different data structures that students like to use here. I don't care which one you use, just get the job done. But some data structure that's going to mark the nodes that have been explored. Visually on the slide, nodes that have been explored are going to be marked in orange, and nodes that are not explored are going to be marked in blue. And just before I get too far into this, I tend to use the word explored and visited interchangeably when I'm talking about this algorithm. So if I use either one, I mean they're going to be orange here. They're marked as explored or marked as visited. And then the Q is going to keep track of the nodes that we're going to visit or explore the neighbors of. So some data structure, a lot of choices here. A set really is like the answer here. A set would be the best data structure. I've never talked about a set all semester, so if you don't want to use that and it's scary, just don't. But a set, you know it from, you know the theory of a set from 191 or any math class. It's a data structure that can't have duplicates, and it's usually coded in a way that's very efficient, and especially efficient for lookups, for dot contains. Does this set contain this particular value? Sets usually have very fast lookup for that, which is exactly what we want. We're going to ask this data structure many, many times, hey, data structure, has this node been visited? If every time you visit a node, you add it to your set, you can say, hey, set, do you contain this node? And if it does, it's been visited. If it doesn't, it hasn't been visited. So very efficient, very nice lookups there. I think what most students do is use an array list for this. It's horribly inefficient because contains is an O of n operation on an array list. But hey, it's 116. I just said, let's save the efficiency for 250. So if you want to use an array list, I actually had to nerf one of my test cases in Autolab. I used to use the full movies.csv and had a bunch of test cases. But everybody using an array list would time out in Autolab because it's horribly inefficient. So I just got rid of that test case. It's problem solved. You can use your array list, knock yourself out if that's what you want to do. I've also seen hash maps here, mapping nodes to Booleans and have that Boolean be true or false, whether it's visited or not. It's a little bit overkill, but it does get you O of 1, so it's nice. O of 1 lookups. But whatever data structure you're using, however you want to code this up, have some data structure that's going to keep track of whether or not a node has been visited. That's what we want to keep track of. And then our third one, arguably the most important one here, is a map that's going to map nodes to their distance. And this we're going to populate as we go through the run of this algorithm and get the distance from the starting node to every node in the graph, or at least every node in the connected component of the graph, or actually every node. And I'm going to initialize every node to infinity. These are infinity symbols. I always get questions on what that is. Those are infinity symbols. If we run the whole algorithm and we never explore a node and we never update this hash map, then the distance is effectively infinity. We can't get from the starting node to that node. In your code in task 8, you would return -1 in that case. So some way to check if a node has ever been visited is something you'll need to do. What I'm doing here is initializing every node to some value. I would initialize that to -1 if I were doing task 8, just because that's what task 8 asks for. And for that, you can go through the adjacency list of your graph. You say graph.getAdjacencyList, get the adjacency list, do .getKeys, iterate over all the keys, and initialize your hash map with every single key in the graph would be how you would set that up. That question came up in the last lecture, so I'll get in and just answer that one right now. What about a hash map of array list? Sure, go for it. For this guy, go for it. Knock yourself out. I don't care what you use as long as it works. We already have a hash map of array lists in representing the graph, the adjacency list is already that. It's not too far out of the question. So those are our three data structures. A queue to keep track of the order of the nodes of which we're going to visit the neighbors of, a something to keep track of the nodes that have been visited, preferably a set, but whatever you're going to end up using there, and then a hash map that's going to map our nodes to the distance of each node. And we're going to initialize each one of these data structures with the starting node. So before we start running this algorithm at all, we're going to process our starting node. You choose one of your two actors as a starting node, doesn't matter which one. You're going to get the same distance number regardless. Mark that node as visited, enqueue it, and set its distance. The distance from the starting node to itself is always 0, so initialize that distance to 0. So that's all the setup. Creating your three data structures and initializing those data structures with your starting node information. Then we can start the algorithm proper, which is going to be a nice application of a while loop. So what we want to do, the algorithm in a nutshell here, is while this queue is not empty, dequeue the first node and explore the neighbors of that node. That's, in a nutshell, what we want to do. So let's start doing that. We only have one value in this queue, so let's dequeue our starting node Carnegie and talk about exactly how we're going to do that. So we're going to dequeue Carnegie. We're going to go to our adjacency list and say, yo, give me all of the neighbors of Carnegie, and we're going to loop through all of those neighbors. There's two of them, Case and Harvard. For each neighbor, we're going to ask ourselves one very important question. Has this neighbor been visited yet? For that, we're going to use this data structure and say, has Case been visited yet? If the answer is yes, we don't do anything. In this case, the answer is no. We haven't visited yet. We're about to visit it. So if it hasn't been visited, we're going to do three things, and those three things are related to all three of our data structures. Mark the node as visited, enqueue it, and set its distance equal to the distance of the node that discovered it plus 1. In breadth first search, and that is breadth first search, we just run that loop. We're going to go through the whole thing, but you would run that loop until it's done, until the queue's empty. Breadth first search is going to guarantee that that will be the distance of every single node when we update these distances. We visit Harvard too. It hasn't been explored, so we mark it as explored, enqueue it, set its distance equal to Carnegie's distance plus 1. And we keep going. Dequeue Case. We're going to check out the neighbors of Case. So Case has a neighbor of Carnegie. And if we were to explore Carnegie at this point, we're not going to, but if we were to explore Carnegie at this point, we would set its distance equal to Case's distance plus 1, which is going to be greater than the distance we already found. Breadth first search is going to avoid this by never exploring a node more than one time. So since we're asking our data structure, has this node already been explored? If it's already been explored, that means we already know its distance, and we're never going to update these values after we set them. We already know its distance, so we don't want to visit it again and overwrite that distance with a larger value. We don't want to say if this distance is less than or equal to the distance I already know. We don't have to do any of those comparisons. Breadth first search guarantees we're going to find the distance when we first discover a node. So we ask this data structure. We say, have we explored Carnegie? Yes. So we do nothing with Carnegie, nothing at all. If we have not already explored the node, so with Lincoln, we haven't already explored this node, so we're going to explore it. Mark it as explored, enqueue it, set its distance equal to the distance of the node that discovered it, plus 1. Because if Case's distance is 1, we can get from Carnegie to Case with a path of length 1, and Case just discovered a brand new node, we take one more edge to get from Carnegie to Lincoln as we did from Carnegie to Case. So we add that one edge, bump that number up by 1, and that's our new distance. DQ Harvard, Carnegie already visited, do nothing, BBN. mark it as visited, in queue it, says distance to Harvard's distance plus 1. And when we have the code, when we have the data structure set up like this, we can see how that arbitrary tie is broken. Lincoln and BBN are going to fight over MIT of which node is going to discover it. And it's going to be Lincoln that discovers it because Lincoln's further ahead in the queue. So you don't have to code this at all. It just is a matter of what order these nodes ended up entering into your queue. And that's going to determine which node gets to visit MIT and which node is going to say, oh, MIT is already visited. But either way, Lincoln and BBN are both distance 2. So they would both set MIT's distance to 3. Doesn't matter which one is chosen if we're only concerned with computing distance, which in task 8 we are. And this arbitrary decision, to really track it back, it was a matter of whether Case or Harvard was added to the queue first. And Case was added first, so then Lincoln was discovered before BBN, and then Lincoln is going to get to MIT. So what actually broke the tie, what made the arbitrary decision, is in the adjacency list for Carnegie, was it Case then Harvard or Harvard then Case? Which is a question of which edge got added first. That's when the arbitrary decision is made. So you're just going to add all your edges in a couple loops and not really care when that decision is made. Doesn't really matter. Nothing in your code has to decide. It just gets decided arbitrarily. I mean, unless you actually did care. Not for this application, but for some you might. So Lincoln gets DQ'd, takes a look at Case and says that was explored. MIT has not been explored, so mark it as explored and set its distance to BBN, Lincoln's distance plus 1, so we're up to 3. And then BBN is going to look at MIT and say, oh man, I didn't get to MIT. Look at Harvard, already been visited. Look at Rand, mark it as visited, in queue it, set its distance to BBN's distance plus 1. And at this point, we can start seeing what the queue is doing for us. What the queue will do is visit the nodes in non-decreasing distance order, which means we just visited BBN, Lincoln and BBN. We're going to visit every node of distance 2, then every node of distance 3. We see we have all of our nodes of distance 3 in the queue right now. After we visit all the nodes of distance 3, we're going to visit all the nodes of distance 4, then all the nodes of distance 5. They're all going to be visited in non-decreasing distance order. The queue guarantees that because we're going to start with a node of distance 0, which in-queues every node of distance 1. When they're visited, they're going to in-queue every node of distance 2, and they just in-queued every node of distance 3, which are going to in-queue every node of distance 4. And this is what gives us the guarantee that the first time you find a node when you run breadth first search, you found it via one of its shortest paths. So you did find you can compute the distance based on that. So MIT, we're going to DQ. Lincoln, already visited. BBN, already visited. Don't do anything with those two nodes. And then Utah, mark it as visited, in-queue it, and mark its distance equal to MIT's distance plus 1. And when I say mark it that distance plus 1, MIT is already going to be in memory. You're going to DQ it, and you have MIT in memory in a variable. You're going to ask your adjacency list. Give me all the neighbors of this node. It's still in memory in that variable. Loop over all of the neighbors of that node, which is still in memory. And then when you get to one that hasn't been visited, you take this node, it's still in memory, still in a variable, and you ask this hash map. Give me the value for this node that I'm currently visiting the neighbors of. For MIT, it's going to cough up 3. I bump that up by 1. And then put into this hash map the node that I'm currently discovering that value plus 1. Put that new key value pair into the hash map. So I'm asking the hash map for a value, adding 1 to it, and then putting that new value into the hash map with a different key. I get a lot of questions about that in office hours, so I'm going to explain the logistics of it. All right, and then Rand looks at BBN and says, already visited, not doing anything, but does get to visit 3 other nodes, mark them all as explored, in-queue them all, set all their distances to 4. Now we explored the neighbors of both of the nodes of distance 3 And what we're left with is all of the nodes of distance 4. That queue is doing a lot of work for us, keeping track of the order to make sure we actually get these distance values the way we expect. So Utah, MIT, and SDC already explored, so we don't do anything. SRI is not explored. Market is explored. Enqueue it, set its distance to Utah's distance plus 1. DQ UCLA, already visited, already visited, already visited. But we do find Stanford, enqueue Stanford, and says distance equal to 5. And we can tell at this point we've already visited every node. So no matter what node we're visiting the neighbors of, they're all already explored. So we don't have anything left to do. But the code is still going to run through the rest of the queue. Remember, our while loop is, well, the queue is not empty. Keep going. So our code is going to go through each one of these, all the neighbors still. UCSB, explored, 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 don't do anything. SDC, explored, explored, don't do anything. SRI, explored, 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 don't do anything. Stanford, explored, explored, don't do anything. So nothing left to do on those nodes, but our algorithm's going to run until that queue's empty, at least in the worst case. Some students like to shortcut it and return in the middle of the loop. But in the worst case, the two actors will not be connected at all. You have to run through the whole thing to make sure that you didn't miss a path. Why wouldn't the code find Stanford from SRI and give it a distance of 6? Stanford to SRI, because at that point, SRI is already explored through Utah. So since it's already explored and marked in this data structure as explored, we say, go through the neighbors of Stanford, check SRI. It's already been explored, so we don't do anything. UCLA, same thing, don't do anything. If we updated distances, we would have got stuck in the first loop. This is where our tree algorithms break down. We would get stuck here. Carnegie, distance 0, finds Case, give it distance 1, which finds Carnegie, give it distance 2, which finds Case, give it distance 3, which finds Carnegie, give it distance 4, and we just get stuck right there, and our algorithm goes for infinity. So we want to make sure we never visit a node twice to avoid that situation where we're overriding the lowest, the distance with a higher number and not getting stuck in any loops. Yeah. If you want to try to use 2, you can go for it.
If it's -1, that means it's not been visited yet.
If that's the way you want to code it, go for it. Yeah, if that's the way you want to code it, go for it. Any other questions? Yep.
Do you recommend building the hash set during making the graph, or not making? I mean, when you're iterating through reference search.
This data structure that I recommend a set for? You would create it before you start running breadth first search. I see this as 3 separate steps. One is building the graph, where you're going to go through all your movies. 2 is initializing all your data structures. That's when I would create the set. Create the set and then initialize it with the starting node. And then in breadth first search, that's where I'm adding nodes to that set. Because then I can do set.contains. Yeah, or whatever data structure you want to use to keep track of that information. Yeah. Yeah, so that node's going to be in memory still. Let me get to, like when we're doing Utah, I'm going to DQ Utah. I'm going to store that in a variable. So I have that variable in memory, and I'm going to hang on to that variable and make sure I don't lose that. And then I'm going to ask my adjacency list for all of its neighbors. I'm going to get these 3 neighbors in an adjacency, or in an array list, and I'm going to loop through those. 2 of those I'm not going to do anything with. But when I get to SRI, it's not marked as explored. So I want to update SRI's distance, mark it as explored, and queue it. But the distance, the one we're talking about, setting the distance, since I still have Utah in that variable in memory as the node that I'm visiting the neighbors of, I can go over to this hash map and say, hey, what's the distance for this node? And it's going to tell me 4. and then I can add 1 to it. I have a reference to this node because I'm looping over it, and I have it in my iteration variable for iterating over my array list. So I can go to this hash map and say, okay, this node's value, it's going to be 5 because you just told me 4. I'm going to add 1 to it, and then put that new key value pair into the hash map. Make sense? Cool. Any other questions?
Instead of using like the dictionary, can these be objects?
You can, bless you. I mean, you can build it any way you want if it works, as long as it works. This is the theory. Like I said, with a few of these, you have a lot of choices in data structures. I didn't give any choices for the hash map. It's pretty much hash map. But I think this way is easier to explain in a lecture, easier to understand in a lecture. That's why I'm doing it this way. There are fancier ways. If you want to do it a fancier way, go for it. But I think this is the cleanest way to explain it in a lecture. Okay, and what we have is the distance from the starting node to any other node in the graph. And you can stare at this graph all day. You're never going to find paths shorter than this from Carnegie to any given node. So from Carnegie to Stanford, or Carnegie to SRI, I'll choose this one. Distance 5, we found this path from Carnegie to SRI. We're never going to find a path of length 4 or less, because breadth first search would have found that. It's a guarantee breadth first search gives us. It will travel the shortest paths. Can you do it with no data structures? Sure. Yeah, pen and paper. Yeah, you can try doing it with no data structures. Off the top of the head, create a node object that stores this information, whether it's visited. I don't know, the queue order would be pretty tough to simulate, and then the distance. It'd be a pain. I think it'd be a lot harder that way, but if you want to do it, if you want a challenge, yeah, do it with no data structures. Do it with just your array list of movies. Do it with just the array list of movies, because you have to have that data structure. I'd be impressed. It would be your reward if you do that. Are objects data structures? That's a deep question. Kind of, but not really. All right, so that's the second one. That's the one that I would expect you to run for task 8. But in the last few minutes, I do want to talk about another thing. I used to require this, but I don't anymore because it's kind of a pain. Breadth first search with pathfinding. We got the distance from the starting node to any node. But what if we actually want the path? What if we want not just the distance of the shortest path, the length of the shortest path, but we want the path itself? There are applications where we want this. Any pathfinding application, we might want this information. I used to require this. It's about as difficult as finding the distance itself. The problem with it is that I found is the testing is a lot more tedious, because you have a lot of situations like this Carnegie to MIT where there's multiple shortest paths. And in your testing, you have to accept any valid shortest path as a correct solution. And I've hit you with that enough times this semester where you have a return value where there's multiple correct return values. I didn't need to hit you with that again, so I don't require that anymore, but it is fun to do. But let's talk about how to do it anyway. How to use this for pathfinding. We're going to keep track, instead of the distance values as integers, we're going to keep track of which node was used to discover each node with a special marker to indicate our starting node. And then each node, Harvard and Case, were discovered by Carnegie, and so forth. Every node is going to remember which node discovered it. Which node were we exploring the neighbors of when we found that node for the first time? And if we run the whole algorithm, I won't go through every single step again, but this is what we'll end up with, is all the data, the node that discovered each node. And then if we want to build the path, say I want the path from Carnegie to Stanford, I'm going to start at the end of the path. I'm going to start at Stanford, my destination, and I'm going to keep asking this hash map my questions of where did you come from? Stanford, who found you? UCLA found me, and start building my path backwards. UCLA, who found you? Rand. Rand, where did you come from? BBN. BBN, where did you come from? Harvard. Harvard, where did you come from? Carnegie. Carnegie, where did you come from? Yo, man, I'm the starting node. And once we hit that special indicator saying I'm the starting node, we're done. And that's how we can build these shortest paths from the starting node to any node in the graph. Storing just a little bit different information here. And we could use this. We used to use this. This used to be the equivalent of task 8. I have a game. It's a 2D top-down grid-based game where you're a player and their enemies. And the enemies and the players shoot at each other. And the AI has pathfinding. When I give you the handout code, they have no pathfinding and you have to build it. But if the player's right here and the enemy is right here, the easiest thing to do would just do some vector math and travel along this vector, and you're going to get caught on this wall right here and get stuck right here. So how do we get the AI to navigate a path that goes from their current location to the player? Well, the AI is going to build the graph of the whole grid. So we're seeing this as the game without all that clutter. And the AI says, well, I'm at this node. The player's at this node. Run breadth first search and find that path, and then traverse that path, which will effectively avoid all the walls. Even if the level is a literal maze, the AI is going to navigate that maze and find the player without getting stuck on walls. Yeah?
What is the efficiency of
O of n plus m, where n is the number of nodes and m is the number of edges. That's a 250 thing. I'm not going to do any proofs of any of that, but because you visit each edge twice, so it's like 2m. Actually, I will do a little. 2m plus n, and 2 is a constant, so we don't care. Okay, great, but we got actors, and we need the degrees of separation between actors. And in 1 minute, oh goodness, we have our data like this. We'll build our graph. Each pair of actors in a movie, we're going to add an edge to our graph. We have the add edge, which adds the nodes. That one method will do all the work for you. So for each movie, go through every pair of actors, build that graph, and run breadth first search. Choose one of those actors as your starting node. Run breadth first search. Keep track of the distance for every other node. And then once breadth first search is done, look up in that hash map the ending node or the other actor. Whatever value is there, that's what you return. That's the int you return. If the actor has never been discovered, or possibly the actor isn't even in the graph at all, like I gave you some actor that's not even in the data, then return -1.